select what it is that you want to minimize, maximize, or hit a target value.
Okay. So it's recording. So.
And then you tell it which cells can be
PowerPoint, your Excel, whatever you want to
varied.
do.
So I need to put in,
Another one up for the pen though.
Z.
Turn the brightness up here.
The wrong one.
Yeah, at least squared error is what I need to put in.
Okay, and then we were gonna
Yeah,
do
this
a
is
short
right.
one to see if I think we're all.
You just make sure.
Yeah,
if
it
you need
was,
to, you can stop it and I can check it on my machine right here.
It was relative error and then squared.
Yeah, just open that up, that open back up. And
So it was
when you're done, just hit stop.
Stop. And then I gotta wait.
it was
till it's done.
actual minus
Yeah.
theoretical over actual,
I promise.
and then squared.
Isn't that how I amended in detail in the library?
No, what it was, he hadn't logged out of the
I
4x4.
can't.
So, not a problem. But make sure you put on the wireless mic.
Oh, yeah, thanks.
Get, yep, just right around that. It's recording. So you should be good to go.
Thanks for showing up.
Of course, if you have any questions, send an email or something like that.
Okay.
Just pick it up for-
All right, so the only thing that may help my Surface Pro is this thing getting
For right
fixed.
now, yeah, you just want to use that. You should be able to do everything you want to do. Have a good one.
All right, thanks. Well, I don't have touchscreen, and you know how that bothers me.
I do.
The thing about touchscreen with the stylus is I can actually draw pictures that show up on the recording. And I know you haven't seen Kaltura yet, but it's not as good as Tegrity. How many people used to watch Tegrity besides Gene? Okay. Tegrity, you can expand the slide or the speaker to full screen. In Kaltura, you're going to be stuck with two boxes, neither of which you can expand. So I was really going to try to eliminate the use of the whiteboard and maximize the use of the screen. Okay, so we're going to start over. We're going to go right through everything we did last week, and then we're going to add on. And part of that's to the benefit of our true distance learner who's in Denver. And we may have another one. I don't know unless they contact me whether they're actually here, because I don't take attendance in this class. So I've augmented the PowerPoint slides based on some of the questions and knowing what some of the background is, like not knowing what a frac job was, or so I've got some pictures. Now I think I can increase the resolution here a little bit by. Isn't that better?
Yeah.
Okay. I can come down more if you.
Yeah, these two things.
You want those little ones up too? See, I don't know what I did here. Okay. And slide. We have to come over here.
So,
Oh yeah, here's your. Those are horrible, aren't they?
Yep.
That one's good. And this. Would you like me to turn that off?
No, I prefer to leave it.
Okay. Now, I can still write on my slides with these pens here if I need to, but you're not as good with the mouse as you are with the stylus. Okay, so we'll go all the way through this production slide. Well, not all the way through this PowerPoint. By the way, this is uploaded, so it's got the same name. So if you want this PowerPoint, you can download it. And also the spreadsheet that's called software, I've added some Visual Basic code to it. It just used to have one module, now it has two. But we're going to be very careful so that we can save your work, because a lot of you probably are not familiar with moving the Visual Basic from one spreadsheet to another. There's like 3 ways that I do it regularly, but I'm going to try to walk you through the simplest way. So we'll start here with the production system. I'm not sure where the camera is. Here we have our reservoir. Okay? And our reservoir, we're going to look at our other PowerPoint that has phase envelopes, and it can contain fluids depending upon the composition of the fluid and the pressure of the temperature of the fluid. It could be oil, it could be gas, or it could be both. But a reservoir used to be a very porous, impermeable geologic formation that was overlain by a trap, shown here in the cartoon as the black layer, usually depicting shale. Of course, now we know that we can actually produce from shales, so the reservoir model has changed considerably. So now a reservoir is, as far as we're concerned, is a geologic structure that contains hydrocarbons. All right? And I've had a couple of people that wanted to meet with me between the last class and this class. And in general, it's not like I don't mind meeting with you. It's just that if you didn't understand something, there's probably somebody else in the classroom that didn't understand it either. So feel free. We have a 3-hour class. It's not like I'm worried about getting done. Okay? Take your time. We're trying to stretch this out. I've got like, 10, 12 slides total for tonight. And we'll do some work in Excel like we did last week. So just feel free to stretch this out. Ask any question, no matter how silly you think it is. You've heard the teacher say there's no such thing as a dumb question. Because the person sitting right next to you is dying to know the answer to that same question. If you don't ask it, they'll never find out. So you're doing your friends a favor if you ask a question. Okay, everybody knows what a reservoir is. I can ask that on the next test, right?
Will you repeat the definition you just said?
A geologic formation that contains hydrocarbons. And then depicted in the slide is this little region right here. You can tell me what those are.
Perforations.
Perforations. How are those perforations made?
Shots.
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 Guns are lower down in the well in the place of fire.
Guns. Would they look like a gun that we'd get in a rifle store?
It's a tubular pipe, bullets inside, and they are giving the signals, electrical signals.
Can anybody tell me what the closest thing in, or actually where they were invented from? What technology did we borrow from?
Anti-tank.
Anti-tank, okay? Because those things that the soldiers used to carry to pierce the metal of a tank worked really good to pierce the metal of the steel casing. So petroleum engineers can thank the military for one thing, but since we got 3 hours, I'll tell one other story. We paid the military back because seismologists in the Gulf of Mexico figured out that they could detect submarines. Did anybody know this story? And so during, I think this is a World War I story. Not that I was around. But so the military was very excited that our industry could detect submarines. That they were doing seismology work in the Gulf of Mexico, and they would see these blips that were moving. And so they got rid of a lot of enemy submarines rapidly with our help there.
Weren't they able to also triangulate artillery from seismic?
I haven't heard that, but it makes a lot of sense that the percussion would put out something with seismic. But I would think you wouldn't need that with satellite surveillance, but I could be wrong.
Well, not today.
Not today. Okay, we got 2 red boxes. So I'll just stretch this out a little bit, but the way this happened is we drilled a well, and when we're drilling, we have this fluid in the hole that we call mud, because it looks like mud, and it is mud. But it's not just water, because typically we have to weight up the water so it equals that bottom hole pressure based on its fluid gradient, the same pressure as the formation that we're drilling through, because if it's less than the pressure of the formation we're drilling through, we have a kick, which could be a blowout. And if it's more than the pressure in the formation when we're drilling through it, we have invasion, or we lose circulation. And this isn't a huge problem. It's not as big a problem as a blowout, but oftentimes we damage the formation so much because we lost so much fluid that we lose our reservoir. And also, we're losing fluid that costs us money. So we try to drill our wells balanced. And then when we get done, we take our pipe out of the hole and put our casing in the hole, and then we circulate cement down, and it circulates the mud up the annulus, and then we flush it with water, and now the cement's coming up the back side. So we got cement between the hole and the casing, water in the inside the casing, and the mud out of the hole. Ideally, that's the way that all works. And then we shut it in and let the cement dry, and so that's what we have in most situations. And a lot of the drawings that we're going to have are going to be about vertical wells, and I'll talk about horizontal wells versus vertical wells at some point in time later in the course. But most of our textbook drawings are of vertical wells. Okay, so this is natural gas engineering, and so what we usually see in the natural gas engineering textbook is a wellhead that looks like this, rather than something that looks like this that we call a horse head, you know, or a beam pump. It's got some kind of counterweight on it, and it goes up and down, right? How many people have never seen a beam pump? Anybody never seen a beam pump driving around
But I know.
in Oklahoma? You haven't seen a
Maybe I
beam
didn't
pump?
know that's what it was.
I don't think your illustration's good enough.
Pump
Am I spitting? Okay, how come when I hit escape, we'll discard them here. We have the internet.
Same thing on Supper Rock Pump.
Oh,
Pump jack.
Yeah.
Yeah.
Okay. Yeah, I was illustration.
Those things.
Yes.
Okay, that's a beam pump. Now, if we're producing primary liquid, this is all important. If we're producing primarily liquid, the liquid gradient in the well is much higher. What is the liquid gradient of water in PSI per foot?
0.435.
0.433 if it's fresh water. A little bit higher if it's salt water.
0.46%.
Okay. What if it's oil?
0.3.
0.3 is a good number. And what about if it's gas?
0.08.
0.08, I usually use 0.1 because I'm not that accurate. Okay, so with the same bottom hole pressure translated to the surface, I lose less surface pressure if it's a gas column than if it's an oil column, than if it's a water column. So gas usually flows to the surface, even if it's lifting a little bit of water or condensate with them. And so typically, but not always, we would depict, how come that 5 doesn't work? We would typically, do I still have a pen? No, I gotta start over.
Download function.
Depict this with something you
Internet
can
Explorer
hardly even
either.
see. You could drive by this on the road and not even see it. Maybe stands this about this high. And again, I'm going to repeat all this when we go through the phase diagrams, kind of what you see at the surface. And I can basically look at a surface and tell you whether it's a condensate reservoir, or oil reservoir, or gas reservoir, just because I've seen so many case histories. So by reverse engineering, I can probably tell you what kind of reservoir it is, because depending upon what kind of reservoir you have, you design your surface facilities to accommodate that kind of reservoir. So this drawing's from our book, right? Didn't I lift this right from our textbook? Maybe not. Maybe I got it from another textbook. Figure 1-6. Is this figure 1-6 in our textbook? No. Sorry. Okay. Now I added this portion of our to our slides from last week. But what we have here is kind of the old school two-stage separation, and really we would really call it three-stage separation because we'd have a stock tank out here, and although we only sent it oil, it's got a vent cap at the top because otherwise on a hot summer day you build up so much pressure it'd blow up. So you got to vent the gas. So this is kind of a old, this is the way most of the facilities were built 20 years ago, about the age of this textbook. Okay, so that's three-phase separation. So you basically try to separate the gas in a vertical because gravity is on your side in a vertical separator. And then when you go to the second separator with just the liquid, you want surface area. You want as much surface area as possible to separate water from oil. And I like this drawing that I have right here because it uses the same numbering system. Oops. How come that didn't come in? Yeah, oh yeah, it came in here. It uses the same numbering system that our textbook uses, which means that it's going to go to a high pressure separator, and then usually the water and oil are not separated at a very high pressure. Sometimes they're even heated up, and it's called a heater treater. And then the stock tank is referred to as the third stage, although it's not a separator vessel, it is a vessel, and it does separate oil from gas. In fact, there's even a liquid knockout at the bottom of it. A stock tank can be a third phase. You don't have your hand in your, okay. So does all this review help a little bit on our surface facilities? Okay. And I mentioned a vapor recovery unit last week, and I got a picture of a vapor recovery unit. So a vapor recovery unit recovers this gas, and why do we not like it to go to the atmosphere?
Because they contain poisonous gases.
It's not so much poisonous, to tell the truth. We really have very few deaths from methane leaking off the vapor recovery unit.
It's revenue.
Huh?
Revenue.
Revenue, except for I can tell you right now that down here, benefits equal cost. You spend about as much money on a vapor recovery unit as you do to put the gas back in there. But you'd run this vapor recovery unit even if you were losing money. And why? Emissions, regulations. And methane is worse than CO2 as far as a global warming gas. And I just read an article this past week that they went over the Uinta Basin, and that's in Utah, and the numbers seem high. Like 12% of the total production from this basin was being lost to the atmosphere. So we don't really like. It's better that we flare it. You know, we look at flares and think that that's really bad, but it's actually a worse greenhouse gas situation to burn the gas and give off CO2 than to actually let methane go into the atmosphere. So for all the reasons, regulatory and emissions, and we're trying to wear less of a black hat all the time. But you know what I mean by that? If you don't, you'll have to raise your hand. Okay, so we have three stages, stage separation. That's going to tie into what I'm talking about in our textbook. Okay, so I'm going to back up a slide. This is right on your textbook. This is equation 1.37. What I want to know from chapter 1, because what I'm going to be doing is reservoir calculations. I want to know what our textbook calls, there's a fluid property here, and it's the gravity, and it's usually a W rather than an R for reservoir, because it's the gravity of the well stream after you combine it. I think, doesn't our textbook use W? Yeah, it uses W. And it doesn't say what W is actually stands for, but I think another textbook, I think it's one of those things that just got in there early, and it was really used when they were calculating flow in a pipeline, it's well stream. But for all intent and purposes, it's the gravity of the fluid, the gas gravity of the fluid in the reservoir. And so if I have to calculate a Z factor, if I have to calculate the viscosity, we learned last week that those are a function of pressure, temperature, and composition. And basically the composition is, the composition can be simplified to the well stream gas gravity and its impurities, nitrogen, CO2, and H2S. So what do I measure at the surface? I measure the gas gravity, and we're using their nomenclature, 1, from a high pressure separator. 90% of the gas that I sell is going to come right off that high pressure separator, and I know that because we have custody transfer. The gatherer is buying that gas, and he wants to get what he's paying for, and so he consistently, maybe daily, weekly, monthly, samples that, depending upon how much it changes, for its 2 things. Impurities, 3 things.
Liquid?
Liquid, what do you mean by liquid? Let's draw this out.
Petroleum.
Well, water content, which is impurities and water content, cost the midstream operator more money, so they're going to give you less money if there's water in it and if there's impurities in it. Okay, what would they give you more money for?
BTU value.
BTU value, and what is BTU related to?
Heating resistance environment.
Composition?
Yes.
So the lower the gas gravity, the higher the BTU?
No.
No, just the opposite. Okay, and then I heard liquid earlier, but I didn't know which one you were talking about, because liquid could be water or oil.
Yeah.
But usually when we talk about oil in this class, we're talking about condensate. We're talking about something that was in the ground as a gas, and when we bring it to the surface, it condensates. Liquid comes out at a lower temperature and pressure. So I will tend to use oil and condensate interchangeably. But the proper term for a gas reservoir engineering course would be condensate. We're not drilling oil wells, we're drilling gas wells. But we'll talk about where these overlap a little bit when I show the other PowerPoint that I kind of went through real briefly last week on phase diagrams. I didn't make any change to that. You don't have to re-download that. Any questions? Okay, so we're going to theoretically you can have a gas off your second stage separator, and you can call that gravity 2, and you could call that gravity 3. And then the oil that comes out of here doesn't have a gravity, it has an API, right? This is fun. I'm trying to write with the mouse. It has an API, and it's using degrees API. And typically, we talk about yield or gas oil ratio, remember last week we went over one's just the reciprocal of the other times a million. Typically, we have a QG gas rate. I'm always going to use Q for rate, capital Q for Q. The textbooks does the same. And then that'd be QG1. Now, there's some gas that comes off of here too, doesn't usually get measured. And there's the stock tank vents, and if it got measured, it'd be Q3. So we have 3 rates, but so we could have 3 GORs. There's only one oil rate, only one condensate. So normally we have the high pressure separator gas sold divided by the stock tank liquid gas oil ratio. And that would be called R1. The amount of gas that you produce from your high pitch stage separator divided by the rate that you're producing from your stock tank.
Why are you not taking the gas volume at the second separator?
Here, and I was hoping I didn't get asked that question. If you would, this gas would have to go through something that looks like this. Although, again, 20 or 30 years ago, if a lot of fields would have a high pressure line and a low pressure line. So your high pressure gas coming off your vessel that's maybe 600-700 pounds would go into the high pressure line. And then if you had second stage separation that had gas coming off it, it might go into a low pressure line so that you wouldn't have to have a compressor at every well site to bump it up to line pressure. But you see at the stock tank, you're down to atmospheric pressure. You have to have a compressor thereby, or within at least a central battery for maybe several properties. But no, I'm glad you drew me out on that one. Historically, we would have a high pressure gathering system in the field and a low pressure gathering system. So maybe one was operating at 700 pounds, the other one maybe at 100 pounds.
So are you saying we could have 2 GOR calculated?
Well, yeah, you do have 2 GORs. You have R1, as we'll see in the nomenclature in the next line, would be the ratio of the high pressure separator to the stock tank oil. Okay? R2, if you had 3-stage separation, would be the gas that was produced from the second stage. And keep in mind that all these gases would have a different gravity. And R3 would be the amount you were vetting or reclaiming from your stock tank divided by the denominator's the same. The denominator's the same in all those.
One?
Yeah. And we can't really add them together because we would lose any kind of mole balance, because who can tell me the transition from of the gas gravities from 1 to 3?
It's higher.
Yeah, they're higher. Rolling off that stock tank, it's coming directly from a liquid. The gravity is usually about 0.1. Coming from the high pressure separator, it's about 0.7. And somewhere in between, like 0.8, 0.85, is what a second stage separator gas gravity would be. So we have kind of a complicated mixing rule to state whether, if we actually had a measurement of the gas gravity of 1, 2, and 3, we have it for 1. But if we actually had the GOR for 2 and for 3 and its gas gravities, we can actually solve this problem. So this is the well stream gas gravity. And in general, it's going to be largely a function of the gravity of the high pressure gas. The less second stage and third stage gas that's produced, the lower the GOR. So think of the R1, R2, and R3 as coefficients, and they become smaller and smaller. Now, this middle term that has to do with the molecular weight and the gravity of the oil. I went through this last week. Of course, if you're watching Calculator for the first time, this is the first time you're getting this, but the oil or condensate in the stock tank was once a gas. So I'm not only adding 3 phase gases together to try to get a mole balance. I'm adding 3 phases, 3 different products from 3 different separators together. I'm also adding a 4th product together. I'm adding the oil. That oil and those 3 stages of gas at one point in time were gas. I'm going to switch from this PowerPoint after I discard my horrible handwriting, and I think I have both of them open. I'm going to come back to this, and I'm going to pace through all the other cases real quickly. Sometime in this 3-hour period, we're going to go through this carefully. But I want to show what I'm talking about when I'm showing the other slides to show. For this course, for gas reservoir engineering case, we're going to take this as our base case. Okay? So what we have, I think I got one more line will come up here. I have a gas reservoir. All reservoirs, you can write this down on the other test, are isothermal. At 1 mile or 2 miles under the ground, you can't change their temperature. They're in a constant temperature bath. They're surrounded by formations of that. So even though I produce them and there's some cooling near the wellbore, you can see that that's why this path of reservoir depletion is a vertical line. Okay? I cannot change the temperature of my reservoir. It's fixed. Unless my reservoir produces 1 billion years, in which case geological time will change reservoir temperature conditions. But the path of production, I not only lose pressure when I come to the surface, I lose temperature. Maybe from 160 to 60, maybe from 350 to 60 or 70 or 80, depending upon whether you're producing in Wyoming, Oklahoma, or Texas. So the liquids we're talking about occurred somewhere coming up the wellbore or in one of the separators and never existed as a liquid in the reservoir, ever, ever, ever. So I know it's hard to wrap your mind around that because you look at that liquid in that stock tank and say, how could that have ever been a gas? Only when it was blended with all those other gases and put under pressure and temperature, going in reverse of that dotted line, was it single phase. But all of our reservoir calculations would require us to know what the composition or the gas gravity and the impurities are at reservoir conditions so we can calculate the Z factor, the formation volume factor, and the viscosity so we can do reservoir calculations. So we're spending a lot of time on this so that we can make the correct calculations. Okay, I'm going to jump away from this. We're gonna do the whole phase envelope thing again because we'll see here that there's other cases that we need to consider. Okay, I got the other one on. Okay, so, oops. Grab my pen again. So one more time, I'm sorry, I grabbed the wrong thing. The gravity of the well stream, because R1 is going to be the biggest contributor. Okay, so we normally have degrees API, and we'll show here in shortly. That if we have the degrees API, that's the only thing we ever measure of the oil. And sometimes you just hear about it as sweet or heavy oil. I didn't mean sweet. I mean light or heavy. Maybe those are the only two broad things. If I think of light oil, I think of oil with a gravity higher than 40, and heavy oil is gravity lower than 20. Okay, you'll never have to punch this equation in. I've done it for you. I think this is our example. So this is good because these are typical numbers. Look how much bigger R1 is than R2. 7,000 to 500. It's an order of magnitude greater. So remember when I talked about this equation that R1 is a coefficient? You can see it's 10 times greater than R2. So your gravity of your well stream is going to be dominated by the gravity of your high pressure separator. Okay, in R3, it's 1/5 of R2. So these coefficients become smaller even though the gravities become bigger. 0.71, 1.02, 1.55. I've actually never seen a 1.55. Okay, and they're giving you your QO and your QG, but we really need to know the GORs. As I go through this, these examples, I'm not going to pay too much attention to these rates because all I'm really after is that well stream gas gravity so that I can do what kind of calculations? Reservoir calculations. Okay.
What we are doing in the equation is actually the recombining.
Yeah,
the two.
we're going backwards.
Okay.
Okay.
So that equation will give the specificity of the reservoir.
Yes, and that's what we're spending so much time on here because all my calculations want to be of the reservoir fluid. Okay, so now, how many people have already downloaded the new spreadsheet called software? I'm just going to go to my file folder and get it. See, I got it right here.
Dr. Powers, it's supposed to be in D2L. Is that what it is?
Yeah. Yeah, it's in D2L, it's just called software, right?
I don't think
Nope.
it's there. There's the new PowerPoint and the spreadsheets are not there.
There's no spreadsheet there?
There's the old
Just
one.
the gas
blue
one.
Oh, it's the same, it's got the same name. Download it, okay. Here, okay, stop. Take your old spreadsheet and rename it old. The one you downloaded last week, just rename it old. Okay, and then download that thing that says software, but I've tricked you. I've added some more Visual Basic in it, and I gave it the same name. It's easier for me that way because then when I upload, it always does a replacement to give it the same name. And when I see we need more software, I'll probably do it the same. So if we learn how to do what we're going to do tonight, save your work, add new software, then you'll be good for the course. So pay attention. So, before you do anything, I'm going to walk you through 3 ways to do this. You can have both spreadsheets open. One called old and one called software. How many people have got both spreadsheets open? Okay, now hit Alt F11. I have to open 2 spreadsheets to do this the reason you want it long. I happen to have two spreadsheets open. I've got the one I use for this course that has as tabs here all the homework problems and all the examples. And then I have this one I just dropped down, okay? And if I hit Alt F11, I'm gonna, I don't like this, I don't like this display. Okay. I'm gonna close that window. What we have here, I can't write on this screen. Well, yes I can. Watch this. Alt screen. I sure can. Okay. This is an important thing for you guys to know, is if you got more than one spreadsheet open, when you hit Alt F11 and go into your Visual Basic, it shows you Visual Basic for any spreadsheet you have open. And you should be able to identify the names. See, here's my gas PBT. I can't, well, hang it. I know what I'm going to do a better job here. Modules. I got both of the modules open now. Now I'm going to do a print screen. Get rid of that old one. I only need this upper left hand here. I did that one. That's fine. Okay. So now I can see that I have two spreadsheets open, and yours is going to look a little bit different than mine right now. But one should just have gas PBT. Does it also have the Chen function? Okay, that's what I gave you last week. And is that one called old? And then you have now one that says gas utilities 5613, which is the course number, and then 2013, that's this year. Does everybody see that module?
Yeah.
Gas utilities. Okay. And this one is the one I asked you to rename as old, right? I want you to move the new software into the old thing. And you can do it just by doing a left click on this and dragging it up here. And then you should see that module twice. Just drag it up there.
Wants to move the old to the new or the new to the old?
Well, you see your works in old,
Uh-huh.
okay? And so I want you to save your work
Okay.
and add to it some software. So all you're going to take from this new spreadsheet is the software. And so if a month from now I load a new software up, you'll do this exact same thing. Open up the workbook that I had you call old. I could have had you call it 5613, or I think I had to use your name or something. You can rename it anything you want to. But don't name it software or whatever the D2L original name was, because otherwise it'll try to overwrite it, and it'll erase your work. So you need to give it a new name, because every time I give you new software, it'll have this name, because it'll be a replacement. And then all you have to do is open them both, hit Alt F11, drag up the new software, the new module, and then you can get out of Visual Basic. I usually use this X right here to be the safe one. And you'll find out that you have all the old software. Okay? And we can check. I think I may have T at F of X, and I don't normally, go to user define. That's the software I got you. And you see, mine looks bad because I have some of the same. I've got to undo this. Oh, all I gotta really gonna do is, I gotta close one of the spreadsheets, because otherwise it will,
Do you know how to move it on a Mac by any chance? Because you can't just.
no, I can't help Mac users.
We just moved the gas utilities one, right? Not the gen function?
You shouldn't have moved, you just, you can leave the Chen function, we're probably not gonna use it this year. But what I want you to do is keep the workbook and the gas PBT, and then drag into it the utilities.
Yeah, okay.
Okay. Now, I'm a little bit different than you guys right now. I'm trying to figure out what I want to do, because I know what I'm going to do here. This is, what problem is this? Example something?
It's 1.8.
1.8, and I'm just going to add something here.
You would do this, he would get it.
Okay, now I'm going to close this. So now, whatever we did before should show up in some other tab, and what we're going to do tonight will show up here. And you can do the same thing I did. I just lifted the information from the PowerPoint with a copy paste into Excel.
Excuse me.
You're not funny.
Pardon?
Can you redo it again, please?
I can't understand you.
Can you redo it again, please?
Are you moving it for the PowerPoint? Is that what?
How many people got it done? Okay, this is how I like to operate, right? Now, how many people are having trouble? Okay, what I want the people that know how to do it to help the people that don't have trouble. Okay, and I'll give you a few minutes to get that done. See, that way, instead of helping everybody, I can get a drink of water.
Okay, one at a time.
You don't have to do it.
Okay, so I just choose this.
Yeah.
Okay.
Okay, look at how this tree is laid out here. You got, this is the old one, because it only has 2 modules. This is the new one, it has 3 modules. I was saying, take the module and drag it down into the old workbook. Without, now you have that there, you don't have to look at it. So then you can just delete the new Excel file that's empty. Okay? Yeah, you delete it because all of your work's in the old file, and now all of the custom programming is in the old file.
So we get rid of this one and move it to here.
Yep.
We're good.
I think all you need to do is, here's what I do. This save button. Okay, yeah. File.
This one is
Oh, okay. Okay, then hit Alt Q. Yeah, if you Alt Q, it'll close it.
This is the old.
Were you able to get it with your
When
laptop?
you pull up and there is the old.
You did it?
Yep.
You guys are reading the module?
You're good. Right.
Oh, I know, yeah.
Like the module name.
So now we're still calling it gas PBT, all we're reading as the utility.
Actually, if I would have had all over, I wouldn't have had to use the term old, I would have had to use the term new.
That's fine.
But, or your given name, or the course name, or something like that, so that I'd like you to have one workbook with everything you're gonna do this semester. So that you think, man, I did that natural gas engineering, I saved that workbook. You pull it up, you rifle through the tabs, so you find out what you need to be able to do, and then you can do it.
That's it so far.
So after we
Maybe something.
export what you want us to, we can delete the new one that we, so we don't have one more.
I can't hear you, you're not loud enough.
I said after we have moved it, we can delete the new one that you had us open.
Yes,
that way we
yes,
don't-
yeah. That's what I did on my screen. Okay, it looks like we're look at that one. The duration count starts moving. I'll minimize that. Okay, so how many people want to make this calculation? You know, if I had everybody do this in class, you know what? Not everybody would come up with the same number. You realize that? In fact, if I did it 10 times, I wouldn't come up with the same number. So one of the reasons I like Visual Basic is that I can kind of duplicate it and find out where my problems are. So all I need is R1. I should have used capital letters here. And I'm just gonna, let's see, gamma 1. I'm gonna be really sophisticated here and come up here and hit symbol.
So you'd be able to zoom in 100% there, would you?
Pardon?
Would you be able to zoom in?
Yeah, down here.
Yeah, that'd be one.
I think I have to get out of what I'm doing. Like that?
That's one.
You like that? And I need API. I don't have it, I don't think. Yeah, I gave him the molecular weight. Okay, R1, 7040. R2 is 510. R3 is 120. Gravity 1 is 0.712, 1.02, and this number seems pretty large to me. And I don't have the API, they gave me the molecular weight. Now, the reason I wrote my VB for API is it's just a linear equation, so I'm going to go get API equals, you can just start spelling it if you know what you want. I want API from molecular weight, and here's my molecular weight. And tell me when you can get 54.572.
Show that again, sorry.
How many people got it? Okay, I'll show it one more time. Okay, I'll show you a different way to do it. And you won't know what these functions are, but they're all user-defined. You gotta make sure you come down here to user-defined. Now, I got an API corrected. You won't have all these. I got my spreadsheet that I'm solving problems in the future, so I got more VB in here than you have right now. But you should have this API from molecular weight. It's pretty self-explanatory, okay? So you say okay, you know, it says what's MDO, molecular weight of the oil. The molecular weight is 125. You say okay, and you get this number 54.572.
Oh, nice. We're on a new sheet, or
Yeah.
this has nothing to do with
Now,
this?
having worked in industry,
Right.
I know what your typical inputs are going to be. You're never going to be told, oh, on that job over there, we had a molecular weight of the oil 125. No, they're going to say that the oil gravity was 54. Okay? Because what they measure the oil gravity, they just put in this special balance, and they fill up a cup of it and put it in a sliding scale that tells you exactly what you. Mud weight's the same way. Okay. How many do not have 54 yet? All right. I can differentiate between the A and the B students already. How many people want help? Okay. Where's our helpers? Help somebody that doesn't have it. Raise your hand if you haven't got it yet. So there are people over to help. All right. You can see it's going to be very difficult to fall asleep in this class.
Did you get it?
No, I'm behind. I went to the bathroom. I missed the whole thing.
Boy.
Yeah, this is all function. Work. This is now
You know, this is just a favor. I just gave you a favor. Did you enter these new values yet? Oh,
this is just
and this is the old. This is the old.
We're going to develop a math users group for this class.
We're figuring it out, don't you worry.
Does all F11 have,
No.
what do?
You go to tools and then macros and then visual basic editor.
Okay.
Those are all different. Like some of the coding stuff is different too. I had to learn that. It's kind of weird.
But all my BB work should work on your Mac.
It does.
If that's a problem, then we'll just kind of get rid of Macs
Well,
altogether.
sometimes though, like another class that I had, some of the stuff that I would upload, I would have to like fix some of the coding because it wouldn't work.
It wouldn't, yeah, it doesn't go the other way.
So I'm gonna have to buy another PC just for Excel.
Well, the thing of it is, when you start work, you'll be given what they want you to have, loaded with the software they want you to have. I think everybody should know how to use a Mac and a BB. I live with my son, he has a Mac, so I know to use two
I love
fingers
it,
to
though.
scroll.
Yeah. Cool.
You're reading the bus already.
I just spending my time figuring out how to get gamma.
He actually showed it.
Oh, did he?
Like type it
Yeah?
and highlight it.
That's not.
Notice this caliber, type in SYM,
SYM?
B,
Huh.
I do the same thing. I might go to inserts and work. I think in the future I'll just.
Okay. Will you catch me up here?
Oh, okay, do a file save as.
You got your molecular weight you need to put in.
What was that?
120.
Oh, okay. I was looking for NW.
API and function API. Yeah, banner. Let's see if that
Wait, I just hit enter. I'm not understanding.
Well, I always click on this. And then
Let's enable this.
User, right?
So yeah,
okay.
this is Excel options.
And then I just
Oh, okay.
I guess you need a
Okay.
I see what you're doing.
Oh, see, it threw me off when it didn't prompt me. Like, you know how when you start a function, like,
Yeah.
it's, that right there, where it's like, okay, no. So, I was like, oh, I must have done something wrong.
And then the next one is going to be, we're just solving for gamma W.
Okay.
And that's going to be,
Yes, finally.
that's a long one.
Yeah.
GWS 3-stage.
Yeah,
GWS, 3-stage.
whatever, that will
And
work, okay.
do you know what's the order of the...
How do we get there? We had to go to the trust center.
Trust center.
R1.
Your
And-
trust center setting.
Trust center settings, macro settings to enable them.
Gamma 1. So R1.
Okay, well, I'll just do it like you recommended.
Yeah, that's why I do that.
I've been using Excel for years. I didn't even know you could do this.
Okay, we'll do it, we'll use this.
GWS.
Launch it.
Oh,
Oh, nice.
Yeah. And like sometimes it'll have like
After
a
that.
description down the bottom too.
Oh, okay, you got two things open, that's your problem. You got two books open. You got two workbooks open. Go all there. You got
Ta-da!
Yeah, if I showed you like my old Excel sheet for this class, and he's right, like we would spend literally an hour trying to solve a problem like this. Like the entire class.
Really?
Because you usually see that. You usually see this. You see you have all these prefixes. Look, this is okay. As if, you need that is
Solve the problem.
there's something else on here.
Go back.
So this function is literally this equation right here?
Yeah.
So what were you saying in your experience it takes so long? Is it like to write this or what?
Pause here.
But say you're not using Excel,
Uh-huh.
say you're using a calculator. You imagine trying to punch that into a calculator.
Now, this is just a predecessor step because what we really want to do is calculate the gas gravity I think we're using 3-stage, R1, G1, R2. See, it gives us a hint of what the arguments are going to be here. R3, G3, and the API. I wrote this with the common input of API, not molecular weights.
The functions there is GWS on each page.
Hang on.
Yeah, GSW3.
Was what?
The function set is 3-stage, GWS, 3-stage.
The GWS is another nomenclature.
Yes, that's the function, boy.
GW or GWS, well stream or well. Somehow this nomenclature got invented by surface engineers and they were just trying to get it away from what they were looking at.
You know, it's sometimes.
I would have called it the G sub, or gamma sub R for gamma for the reservoir. So you'll see GW or GWS. Okay, so I think you're getting the idea that Visual Basic on these more complicated things are important, or make these things a lot easier to use. And then we can also do studies. Okay, so let's study the effect. Now, what I'm going to do here, you don't have to follow along. I'd rather you just watch and pay attention. I'm going to highlight all these things up here and hit F4, right? Everybody knows what that does, right? Made them all absolute addresses. Now I'm going to make a new column for API, and I want to see what the effect is, 20. And then I'm going to move my number down. Well, let's copy this. Okay, I'm going to get the same number, but now I'm going to drag my API that I've been getting and put it over here. And it's that last entry. And I'm not going to make it absolute. Where's scatter? Insert table. Charts. Here it is. Okay. So this would have taken me considerably more time if I had to type in that equation and fill in the numbers every single time. So now I can see that the effect on well stream gas gravity with API. So here I'm in this 55 range. If my API gravity was considerably higher, if my API gravity was a lower number, I could get from a heavy oil like 20 or 30. I like it where I can write on the slide.
Your gamma WS, which was that stage 2, 3, or the GP?
Well stream. For recombining the oil and all the gases together, once it's back in the reservoir, that's the gravity of the fluid compared to air. The specific gravity of the well stream is compared to air. So these numbers greater than 1 means it's denser than air, and numbers less than 1 means it's lighter than air.
I meant like whenever you were solving it in your Excel,
Which
user
variable,
defined function.
she's asking which variable was it in your list of
Which one's the gamma W?
Yeah, I have several. Can you use a defined function?
Yes.
I'm lost.
Okay, if you can just hover over your gamma WS.
Yeah, that's the equation.
Okay, thank you. That's all I need.
What's the second?
The third stage.
GWS 3 stages. See, it's calculating the well stream gas gravity as if we would know all that data, which is a rare situation. Here, in a few minutes, we'll look at the more common situation. But in the meantime, I'm trying to show you the utility of being able to use a VB function so that you can actually study variables and their impact. Because this would have taken a lot more time.
Thank you.
I don't have great graphics right here. But as my API was way up in this range. But if I had all the other things were constant and my API was lower, if I was mixing in a much thicker liquid, it would have raised my from 1.08 to 1.3. So you can run sensitivity analysis on all of these variables. And I got to tell you right now, that's what your tests are going to be. I'm going to ask you to utilize these things to expand your knowledge, to do a little study of the variables. So it's not just to put in the variables once and get the answer once. It's what I just demonstrate here. Let's look at what the sensitivity of API gravity is on the result.
It's more or less like saying at different values, we should make a kind of a comment of what we're kind of witnessing. Is that what you're saying?
In some cases, the study can be very revealing. Like in many cases, when you do this kind of study, you might have a maximum, and that maximum may represent an economic optimum. So one of the things about having these functions built in is that we can use them to design. Okay? So engineering is not like a cookbook where we just take a cup of this, a pound of that, and mix them together and put it in the oven for this amount of time at this temperature. So a chef varies the butter that he puts in that cake every single time he makes it until it's perfect. Basically, for a chef, being perfect for an engineer is optimal.
Okay. So one can from the sensitivity analysis, one can, when you say something about the economic, involving the economy into it, one can draw a conclusion as what kind of surface facility one can build based on that area.
I don't have a good example for the data here. I'm just running ahead, showing kind of the utility and ease in which you can manipulate now that you have a somewhat complicated formula in a very simple function. So I want you to get familiar with the functions, what their inputs are, using very concrete examples from the textbook where you see what they name the inputs and how they're named so that you can use it in a more general. So what you're asking me is what I might write for a test question. I haven't even thought of that yet. And I don't even know which one of these I might use. But I wanted you to get familiar with this type of advancement or use of the being able to do a sensitivity study.
If I'm getting it correctly, I think he's trying to say that when we have the necessary data from our reservoir, if, for example, we know the gas oil ratio, we know what we're expecting, we're able to design our surface facility, like a separator, be able to handle what composition is coming from the reservoir. That's what it's trying to translate from the reservoir.
Okay, you want to talk about visual basic. Okay, let me try to sum this up a little bit better. Let's go offshore. Okay, because as we know offshore, a production facility in the drilling are sometimes a year apart. Because you may have a drill ship that drills the well, and then they move on. And it might be a whole year before they come in and build a platform. And when they build that platform, they have to design the production facilities to be very optimal. Because it's expensive building a platform. And you think rent is high in New York City or San Francisco or Tokyo, rent on a drilling platform in the middle of the ocean is the highest rent there is. If you're the engineer and you say, we need this out there, you better be able to justify it, okay? So you want to have exactly, I'm not even close, but exactly the right vessel. So when you drill this well, you probably test it. You probably flow test it, you get an idea what the rates are. You've got to make all kinds of reservoir engineering calculations and determine what the projected production rates are going to be over the life of this well. And then you've got to define the vessel that's going to optimize your net present worth, or maybe some other economic yardstick like payout or rate of return, that whatever your company's objectives are to maximize. But everything about that reservoir performance is going to go into the facility design. Reservoir engineer and facilities design engineer have to work very close together. Where am I? I think we're ready to do the next problem. If there's no questions. This is the one we just did. Okay. Now, we don't normally have two-stage separation in the field anymore because we're building better vessels. It's like we now have hybrid cars that run on electricity and gasoline, right? So now we just usually have one separator out there. And it separates very efficiently everything we're going to get from the well. Water, gas, which is now condensated into two phases, liquid and gas. Okay, so this is just a little schematic of how the water and oil, by the way, that my cursor doesn't show up in PowerPoint. There's my water, there's my oil, and there's my gas. So there's a dump for my oil, there's a dump for my water, and my gas goes up the same. So this is three phases. It's separating three phases, but we're still going to call this two-stage separation. Because we still have, what happened? That was weird. No. Oh, it was animated on the previous slide, so I copied the animation. Okay. So we're still going to have a second stage of separation because our stock tank, in fact, what I've got up here now is probably a pretty modern installation. One stage separation. The liquid goes to the stock tank, and the stock tank probably has a vapor recovery unit on it. Okay, but by and large, the only thing we're going to measure is, I would say for the last 10 or 15 years, is we're going to get the separator gas gravity because we sell it. And the midstream purchaser has to know what he's paying for, and so they're going to know that gravity and how much there is. And we sell the oil, and oil price is going to fluctuate on, I'm asking those that might know. What? Impurities may bring down the price of oil. API gravity. So refiners always like a certain API gravity. Okay? Now, it's not always the same API gravity. You hear about in the Gulf Coast that a lot of refineries were built on around Middle Eastern oil. So they like that 40 gravity oil that comes in from the Middle East. Well, it's great because the Bakken Shale produces the same gravity, so those same refineries like that. But if a refinery is built around heavy oil that used to come from Venezuela, it costs too much to retool the refinery. So they may pay more for 30 gravity oil than they do 40 gravity oil. It depends upon how the refinery was built. Again, we're back to these design problems. In general, 40 gravity oil is worth more than 30 gravity oil, but it depends. If you're gonna design the thing that gave you the best products that you could sell, jet fuel, diesel fuel, gasoline, some type of lubricant. If you looked at the market and saw what sold the most of, and then recombine it back and what gravity oil would be the best thing to start with, it'd be about 38, 40, 42 gravity oil. But once you've built your refinery to handle 20 gravity oil from Venezuela, you're stuck. You're going to spend more money for 40 gravity oil to get the same stuff out. Okay, so everything I just talked about is kind of a gray area to kind of get you to the point that there's no perfect API and there's no perfect refinery, because things are always changing. Okay, so we're going to look at the next problem, and we're going to use these two terms that we'll never actually see: VEQ and GPA. And VEQ is the volume of secondary separator gas and stock tank gas, plus the volume that would be occupied by a barrel of stock tank oil. So again, we've got separator gas, and we know that we've got some gas that comes off these other stages. What would it look like if it was back in the well stream?
Sorry, you said VEQ made of 3 oils, 3 components. Can you say the third one? You said one was stock tank oil.
Actually, I'm going to grab my eraser here because and this may help. Let's start with GPA. I'm just going to go through this one more time. Additional gas production. That's in addition to the first stage separator. And maybe if I just utilize my animations here. This GPA and VEQ that I just calculated and read in their equations have to do with 3-stage separation, what we're not going to talk about. But we are going to talk about 2-stage separation. And so I actually have a different equation for GPA and VEQ. You don't even need to know the meaning of these right away, because all we're after is this wellstream gas gravity. So what we have in equation 1.41 and 1.42, which we're not going to use in this course, but might be handy for you in the future if you run across this situation. But the common case I see is for 2-stage separation, which is depicted on the previous slide, of 1 separator and 1 stock tank. 2 stages. And I like their nomenclature here because in these equations up here, you have to know that temperature and pressure of 2. PS1, isn't there a P2 in here? Pressure of the separator. Temperature of the separator. Temperature of the separator 2. 1. How come I don't even know the pressure of the second stage separator? I don't know. But anyway, we're gonna concentrate on this area right here. We're gonna subcalculate a GPA. We're gonna subcalculate a VEQ. We're not even gonna see what they are. I don't even care what they are. But we're gonna utilize this equation that uses GPA VEQ, and we're gonna calculate the well stream gas gravity from one GOR, R1. The gas we sell from the separator compared to the oil we sell from the stock tank. By and large, that's the only number I usually have. Okay? And
I have a question.
yes,
This may be not the smartest question, but are you using GOR and like R1 interchange?
oh yes, I am.
Okay.
R and GOR, I am using the interchange.
Okay. Gotcha. Thank you.
I didn't know that.
See?
Oh, yeah.
Questions are the language of the classroom. And like, the further I get from being removed from first learning this, the worse I am at assuming that you know everything, okay? So please ask questions, especially since we have people from different disciplines. So again, this equation's useful. That last equation actually isn't that useful. It may be useful for doing a study, like I demonstrated, but this is the information I always have. If I'm in the field, I can call the district engineer and find out at what temperature the separator is operating at. And I can ask him what pressure the separator is operating at. And what they do is, those are two things that they can control. They usually start with temperature at ambient temperature, which is hotter than surface temperature because you're bringing a heat source up from the ground. So if the ambient temperature is 70 degrees, maybe it's running 90 because it's coming from 160, okay? So maybe that's an elevated ambient temperature would be this separator. And then the pressure, they have control of. If they increase the pressure, then they may get a different GOR or R, okay? In fact, usually there's an optimal curve, okay? If you run at too low a pressure or too high a pressure, maybe, because what are we after? We're after liquid. So most of these optimizations, especially now, with gas less than 4 and oil over 100, the situation's never been this drastic or dramatic in the past 40 or 50 years. That oil is this much more worth than gas. So everybody's out there tweaking their separators today, because some separation, pressure and temperature will optimize how much of the heavy ends of the gas will cling to the liquid, maximizing the liquid volume. Now, it will bring up the API of the oil, but it's not going to do it to a degree where it's going to hurt the price, because $100 versus $4 is just too huge of a difference. And then, so they'll optimize this pressure to get the most liquid, and then they may turn the burner on and run this at a different temperature, and then re-optimize the pressure and see at a higher temperature if they can even get a higher liquid yield, which is the reverse of, or inverse of GOR.
So are you saying to adjust, to optimize the product to GOR by adjusting the pressure? You're saying something about owning the burner, so invariably influencing the temperature as well.
There's some optimum temperature and pressure to get the maximum amount of liquid.
Okay. So it's not categorically only the pressure, so we are actually tweaking.
Yeah, you can check, yeah. Typically, if you're doing this trial and error, you'd run this in ambient conditions because you're not using any fuel to heat up the vessel. Maybe you get satisfactory results then. But then if you turn the burner on, maybe you can get better results. But typically you start at ambient conditions. Now, Having said all that, as if we do everything by trial and error, that's not always the case. It depends upon whether you're a small operator out here in western Oklahoma, or you've got a well that produces 1 million barrels a day. Because, that's a little bit of an exaggeration, but some wells produce 20,000 barrels a day. Okay? Then you would probably use a simulator that simulates all the things that happen in that pressure temperature vessel. And then you wouldn't do this trial and error. You'd have a real good idea of what operational temperatures and pressures and probably what size and whether chemical additives which bring down the foam or the interface. See, I can speed up the volume of fluid that goes through my separator if I can reduce the layer of foam between my oil and water. Sometimes I do that with electrical current. Sometimes I do that with a chemical additive. But if I can do either of those and increase the output, I'm increasing the benefit of the operation. So all these things, but I'm telling you, if you're working out in the panhandle of Texas, you're not going to be using no simulator. You're going to go out there and try this one day and try something else the other day and figure out what works the best. So we solve engineering problems all the way from trial and error. Actually, they like a better term. They call it successive approximation. Okay, so now we're going to look at doing the same thing. Now I got to capture two things. How about this? Let's put it on the. I'm in copy mode, see, now I can't get out of it. I'll zoom back in here in a second. Where am I? How do I move my? There we go. My vision is not what it used to be. Okay, I'm not going to use these things. Now the other way to do this is go solid point. Now, try to satisfy everybody. Okay, R1 is 7040. Look at this. Same reservoir. Okay, we don't know R2. We don't know R3. Gas gravity is 712. It's the same. See, it's the same problem. And we don't know gravity of 3. And this was an absolute equation. But I'm not going to use it anyway. And we know the API is 55.8. I don't need to know the molecular weight of the oil. This is good. We do know the API directly is 55.8 degrees API. Now, we now have some new additional information. See, we don't know R2 and R3. Typically, you don't know them. You don't know the gravity of 2 and 3. Typically, you don't know. But you do know the temperature of the separator first stage. Oh, I got the wrong symbol in there. And you typically know the pressure of your separator. Okay? Oops, wrong one. That vessel has a temperature and pressure, an operating temperature and pressure. Somebody's, at some point in time, attempted to optimize to get the most amount of liquid. Now that I've got it optimized, I know what it is. It is 700 psia. And its temperature is 9 degrees. Do they have the heater on or not? No. I mean, I typically see the separator vessels at 90 degrees. That's even though it's not 90 degrees out every day, you're bringing heat up from below. So it's always hotter than ambient temperatures. No heater treatment. Okay, now the well stream gas gravity.
That's good.
Yes. Didn't want to see the answer, huh? The suspense. You like to draw out the suspense.
Yeah, the pressure of the separator, you represented it with S2, in nomenclature S2. And what is X1? I mean from what you typed on your Excel sheet. I think that was S2.
S1?
PS, your pressure.
PS2.
Down.
Use the PS2.
Down.
Down.
I can go down.
Or
The temperature of the separator.
down. One
Down
more.
again.
Right there.
The pressure
Of the separator. You represented it with an S2. I mean,
Oh, I'm sorry. Oh, that's because I dragged it down and it automatically increased it. And I didn't notice it. See, normally I like that feature. See, normally I like that feature. But I was trying to, you know, with me it's all about keystrokes. How do I get this done with the fewest amount of keystrokes? So, so you caught me cutting corners. Okay. Now we'll use another function, and let's see if I can remember it. It probably starts with G, W. Okay, it's this GWS using this GPA VEQ. No, it's this two-stage. It's two-stage. Yeah.
No, you have to do the GP.
I'm thinking it's this one.
GPA first.
No, I don't. Because I'll show you.
GWS two-stage?
Yeah, I'm using two-phase. This is the one I like. No. That's not it. You guys.
Shouldn't you use the GPA since you have to calculate the GPA then the VEQ?
well, I get to calculate the VEQ.
It must be the VEQ. Let's see what the prompts are.
But I get to get values for the VEQ.
Yeah, here it is. It doesn't prompt for GPA and VEQs, but my first thought was right. So it needs R1. It needs the gas gravity. It should be prompt for G1. It needs the API, and it needs the temperature and the pressure. And what did they give?
Same thing.
1.112. Now, you notice they calculated a GPA and a VEQ. Look at that page of calculations. Who would want to do that? Okay, who'd want to do that? And I'm telling you, if I had everybody in this classroom do it, I wouldn't get the same answer.
Confidence.
So, and then they're just going to use that VEQ and that GPA. And so let's look at the Visual Basic for a second. Now that we know which one we're looking at. It's the utilities one. So it pretty much looks like the equation. Here's the important thing, the reason I showed you. You can use a function. See, I have the functions GPA and VEQ, which are just the equations from the textbook. I know this is going to show up really well. 1.43 and 1.44, they're just the equations typed in. And really, you have to have the right answer at least once to check, make sure you got all the numbers in once. But basically, if I can match the VEQ and the GPA once, then I'm pretty sure I didn't miss a decimal point or transpose some numbers or do a 6 instead of an 8. But then after that, I have a lot of confidence. But if you type in the equation every time, I never have confidence that I typed it in right. But once it's checked, then I'm pretty sure my visual basic. So once you have visual basics that you have confidence in, you can get through your work a lot quicker.
Do we?
Yes.
Will we ever have to create these, or do you always get with this?
What do you want me to do? No. Here's what I'd like you to do.
I just like.
I would like you to learn enough about this so that the light bulb comes on sometime when you're in your first year of work that, you know what, if I just wrote a little visual basic function, this would make my life a lot easier. And I've got a ton of templates back here that I could use. It's almost like that one. It's almost like this one. If you look, since you've asked the question, if you look at gas PVT, these critical temperature and critical pressure, pretty straightforward. Z is Newton-Raphson iteration. You ever need a Newton-Raphson iteration problem? See, it calculates a derivative here because your next best guess is your last guess minus the derivative times your something. And so it uses Newton-Raphson iteration to calculate Z using the Benedict-Webb-Rubin. Viscosity, straightforward. Gas compressibility uses your Z function. Pseudo pressure, you got what you got right here is numerical integration. You've got almost all your examples of for loops, do loops, while loops. I don't think I have too much in arrays.
Do you guys have to take?
But if I went to math, which you might get something, I don't have right here.
Take over methods, or you do some programming in there.
But
Oh yeah. Okay.
my hope is that you'll, in your work career, that you'll realize that this is going to make your life easier. But no, I don't make you write. And mostly because
Visual Basic.
I've taught this class now 7 years, and I assume that the new students got all the stuff from the old ones, or at least half of them, and I don't want to handicap half of the class. Okay, where are we? So, that's pretty much where I wanted to make sure we were at. We know how to update our software. We know how to run some sensitivity. If we wanted to run sensitivity on this one, on API, let's do a what if, okay? I'm going to go with 90. I'm going to pretend I do not know the separator my pressure. My separator pressure is. Okay? This is exactly how my mind works on how I write tests. Okay? So, I'm going to ask you on the test what the separator pressure is. Here's how you'd solve it. I may not ask another, I'm giving it away, but this would be very similar. Remember, this is actually the same fluid, right? And with this calculation, I got this number. Okay? So I could give you all this information. I could give you all this information, right? Just like you were given in this example. I could give you all that information and ask you what the separator pressure is. Okay? Here's how. I am going to get rid of this chart.
Hey, can you tell me what exactly are the Q's right here?
And I want to move these things a little closer together. I'm just going to note these. Everything else go.
Now, one of them just looks like a volume. The capital Q just looks like a volume, is that
Okay.
right? Yeah. And it's volume.
I'm going to
of-
ask you what the separator pressure is. We don't know
Dry
this,
gas.
right? We can't even make, well, I'm going to say data.
Flow stream. Flow rate.
Where's my what if?
Or actually, okay, so
What if? Goals.
Okay. And then
I'm going to say that I would
capital
like
Q, is that the
this
volume of separator? What is that?
calculation to yield a value that I like, right? 1.08. 1.08, we'll call it 1.087. By changing the separator pressure. It's not doing a very good job. I can write, one thing if I write my own, I'm gonna have to cancel this. Oh, it found one. It actually found one. If I didn't use goal seek, I wouldn't give you that problem. Obviously, I won't get a problem. I could do it a different way.
What did you get?
This would be for the
Huh?
QG web.
You got 229?
Yeah.
So whatever they have on there.
I need to look at this function. Oops.
Cumulative gas production for what time period?
The same cell they go, we shall, or what we sell. The blank.
Here's the other way to do it.
Since like inception of the since start of production? No, I mean 2 days. Not even. Well, it's dry gas. Cumulative production. Cumulative dry gas.
Okay, I'm going to make everything absolute. Remember, I did the same thing before. And then copy it. And then make my separator pressure a variable. I got to make sure I hit F4 enough times that I lose all the dollar signs. And then my gas gravity as a function of separator pressure. And you see, it looks like I got to go a little bit lower. Now, in the problem I gave you, I tell you that you were running at 90 degrees. So let's see what my gas gravity looks like as a function of, okay. So one of the problems here is, and then we can't really, we already knew in advance that we're getting two different numbers. So one, I'm going to put this, easy for me to say, I'm going to select the data that work. We know that 700, where is it?
Well, stream gas gravity. So is that the reservoir gas gravity, or is it, we're talking different things?
Yielded,
Well, he's calling it stream the reservoir. What calls it reservoir?
Well, the books are calling it well stream gas gravity.
But the problem.
you see that my solution set isn't on there. If I vary my pressures, I can never hit 1.08. And so this is the solution to the second one. So I would have checked this problem before I gave it to you on a test, but do you kind of get the idea that you can either using, last week we used goal sequence, let's use goal
Okay,
sequence.
so you don't think they're
I
different
mean,
things?
solver. Let's instead of using goal seek, let's try to do the same problem using solver. You're still not going to get a good answer, but it will converge. I believe it will. So let's set this up for solver.
Reservoir gas gravity. This, they're talking about the well stream. Does your legend? What does your legend say about PE5613?
Let's make sure we have it. Where's data? Okay, so this is good because the guy watching from Denver can see how we did this.
I was asking about that. He's calling WF.
So here's solve that in.
That way there's
Go.
no confusion.
So,
Yeah, but W.
by the way, in my undergraduate class, we used the analysis tool pack. I don't know if we'll ever use it here. Now, solver. We want to set our object. Oh, we gotta set up a cell first. Whatever we get here, we want to be very close to 1.08. On a relative basis, we always like to solve things relatively. And what happened there? And then we can take the absolute value of this, but I typically just square it so it's a positive number. Because you don't want to minimize something that can go negative. Okay, let's try to use solver and see what we get. I want to set this cell here, I-12, to a minimum by changing the separator pressure. Lose power, you looking for a power cord?
Yeah.
There's one in the middle of the room, there's one over here, and there's one way over here too. Okay. Solve. What I got to do. Let's see what it gave us. Oh, I got 0. All right. So I would have to test the problem. I would give out for a test. But I just kind of wanted to show you how my mind works as far as I show you how to make the cake with the recipe, but then I ask you to become the chef. Yeah.
You know how we did the tabular form there, and we had a local minimum where we could never get to 1.08. It didn't look possible. Is it?
Yeah.
So, kind of made sense to me that the solver wouldn't be able to find it.
Wouldn't be able to find it. I would have thought I would have found something as close as it could. I would have thought solver would have done a better job.
Because like Goldseek got that 229 pressure.
Yeah.
But then if we look between 2 and 300 on our graph.
Yeah, doesn't even look good.
Yeah.
But you saw it gyrating. When I see something gyrating like that, I know that there's a problem. So part of the problem, there was not a solution set.
So graphic, you can kind of see, okay,
Yeah.
now it's possible.
And we saw that using one method versus the other method gave us 1.08 versus 1.11.
Yeah.
So, and the second method used correlations, but I had kind of thought that there'd been a lot of sensitivity on the separator pressure. Now I can try to do this again with separator temperature, and maybe I can. Get a little bit of time. I like to play.
So I have a question.
Yeah. You didn't want me to play?
No. You. As regard the gravity, the specific point you're using, you said 1.08 and the other one was 1.11. What is the main reference point? Which one are we referencing when we want to use the
We would have to say that one to the left, was that 1.11 or 1.08?
Yeah, I just want
Okay.
1.08,
so that is what we're referencing.
that was a measurement.
Okay.
There's some correlations built into that because
I'll stick with what we have.
okay. That correlation for the molecular weight of the oil from the API of the oil, that's based on data and a good fit of the data, but it's not an exact molecular balance, okay? It's still a correlation, but it's far better than the correlation from the second part of the problem, where someone just made a lot of measurements on different separator pressures and temperatures. The scatter would have been a lot more on that. So if you ask me what my best estimate, let me Control Z and get my numbers back here. I don't know why I can't get, okay. Based on the information I have right in front of me, 1.09 is a better gas gravity than 1.11. So I was calling the number on the left real.
You're looking at the lowest point on your chart there, or?
Yeah,
Gotcha.
that's what Goal Seek came up with, right?
Yes.
Okay. But let's just, for the heck of it, while we're playing around here, and then the other thing is you can do this manually. See, I can bring that 1.11 down by just manually changing the number, right? Okay. Let's go back up to 700 and assume that what we don't know is the reservoir, is the separator temperature. You know what? There's a possibility there's not a temperature gauge on that separator if it's old. Those things cost money. And the pressure range is considerable. Temperature doesn't change that much, so maybe there's no temperature gauge. So maybe someone just gets 90.
Sorry, is there a reason why 0.09 is better than 1.1? Any theoretical reason why you choose 1.09 is better than 1.1?
Based on the information that I have in front of me, in my experience. I know how this data came about. Those types of correlations, maybe it's probably an engineer from a big company, maybe one that doesn't exist anymore, like Amoco. They had all those separators and things out there. And what they did is they tried to correlate the stuff they usually didn't know by measuring when they did know. So they went out there and made measurements on second stage separator gas gravities and GORs. And this end effect, this stage 1 GOR and this end effect API gravity, these were typically the second stage GORs and gravities when I measured them. So this is a fairly loose correlation.
Understanding the kind of shape, am I understanding right, is that we want the lowest gas gravity, because that means the heavy components are in a liquid which were optimized. So
I don't know the answer to the question, but it's very important that you notice that there was a local minimum.
Okay.
Because if there's a local minimum, that may lead to a local maximum of revenue. Okay, so that's the important concept. Now, whether I can follow that logic, you know, I want to jump on that point first, but now let me try to jump on your logic. What you would want is the lowest gas gravity, because that means more of your middle components are over in the liquid, which would expand the amount of liquid you have. So you've got it right on. Yeah. These are the types of things. So the way I would really write this question is I'd give you that data there in the second example, and I say, what is the optimum separator pressure for maximizing revenue? That's only because we were able to notice we had a local min over the operating pressures that I can probably operate this separator.
Okay, so what about the situation? You say you're going to give us that information, the first one. where the gas gravity is 1.086. What about if we run our iteration and we could get a lower value as compared to the one you gave us? Should we go for the pressure for that lower value? You understand?
I'm assuming that these two data sets are coming from the same well at the exact same point in time. And what they've done is they've measured the gas gravity from the second stage separator and the GOR. And then, so on one, they're showing you what the result is using this equation, but then they're not giving that information and showing you what you get if you use the correlation. But the the fact of the matter is, just because I change, this is not a design calculation, just because I change my separator pressure in this equation
as a function of pressure
by
like I just got to this
from
point.
700, let's say, to 500
Yeah.
pounds, that does not
Awesome.
necessarily mean that my gas gravity actually will go down and my liquid volume will go up. It's not a simulator. So, and my mind was kind of going back and forth on that when you first noticed the local min. So, it could be that if we lowered our pressure, we would get more liquid. But before I spent a lot of money, there's a lot of desktop free simulators for separator conditions. I probably want to check it out. And you know who gives you this stuff for free is the people that sell you separators. Same thing with, you know, pumping units. You can get a lot of design software. They want to load you up. Lufkin wants to load you up with pumping unit software so that they will always show that you need a Lufkin pumping unit. But there's software available to even to engineers really on any budget for design. But again, I will try to draw out additional uses from anything that we've done, so that you're just not repeating some calculation like we did tonight. Okay, I promised you that I would go through the phase diagrams in a little more detail. I think we're ready to leave spreadsheets. I think I've done everything I want to do on this spreadsheet. There's one more slide here. Yeah, that's it. I'm going to close that. No, I'm going to do a file save as because I had current folder, and I'll call it class. And close. I don't know what I want to do, just decide after class. Okay, phase diagrams. Okay, this could be propane. It's a single component system. It can't have two phases at any given temperature and pressure. It's single phase. There's no phase envelope. Okay? So propane, I like to think that's a good example, because you know, you can get propane for your barbecue, right? Those little bottles. How many people know what I'm talking about? Okay. Is it liquid? In the bottom. Yeah, it's a liquid. So we don't have to put a lot of pressure on it to make it a liquid. But then as it comes through its regulator, comes into a much lower pressure, it becomes a gas that you convert. So propane's just a really good gas to talk about as far as your ability to visualize it both in liquid and gaseous form. Methane's pretty hard. Methane's hard to get to liquid. You can't get it to liquid without reducing the temperature. Okay, so where's my pen? So this is like that path of depletion in that phase envelope. Anything to the right you'd call a gas, even though its density changes with pressure and temperature. The gray scale here is density. So that's why this is a liquid odor, isn't it? Yeah. And then that would be your bubble point, and then you start having gas. So this is gas. And you know, I've never seen the experiment, but I've heard it done at some of the petroleum engineering schools where they'll take a gas and they'll put it in this window or this cell that you could see into. You've heard of this? And they'll increase the temperature. And it looks the same, because you can see on the density, it doesn't even change that much. And then they'll raise the pressure. You're not really seeing anything happen. And then they'll reduce the temperature, and you still don't see anything happening. And then they reduce the pressure just to about where they started. You never really saw anything happen. And then they open it up and it's a liquid now instead of a gas. But of course what they do is they start here and end up here. So both near ambient conditions.
So what's the nomenclature? Because I always get confused.
C is critical.
But are we calling that just a fluid? Or are we calling that like something that's super critical that's in that, are we calling that fluid? Or
I like the term fluid.
Okay.
Is it necessary that depletion path should always pass through the critical point, or can it be away from the critical point?
Can we jump into phase envelopes? Because we never have single component systems. Okay, so now there's an envelope. Because at some pressure and temperature inside the phase envelope, we have two phases. We have gas and liquid. Okay, now tell me what your question is.
My question is that, I've seen most of the phase diagrams, they are showing two paths. One is the depletion path of the reservoir.
Yeah.
It's a straight line,
Yes.
isothermal line.
Yeah.
And it is always passing through the critical point.
No, it doesn't. I can have a path of depletion here, here, or here.
Yeah. That was the question. It can be away or on the right or left side of the critical point.
This one right here, that's outside of the critical point. What about it?
Got the answer of my question. Actually, what I was understanding that this isothermal line has to always pass through the critical point. But it can be, as you said, it can be, on the left side of the critical point or right side.
To the path of production, the slide I showed earlier tonight.
Not necessarily should pass through the critical point.
No, it doesn't have to.
Yeah.
Nothing goes through the critical point. That's just some arbitrary thing, okay? But it's usually to the left or the right.
Yeah.
The chance of it going through the critical point is like me throwing a penny over there and landing in a wastepaper basket. That's not going to happen. Nothing actually ever goes through the critical point except for theoretically. Don't try to take your mind there. Okay, so let me get rid of my lines. I got it wrong. Where's my pen? Oh, right here. Okay. I'm just gonna go through there's your, this PowerPoint kinda is to define the difference between an oil reservoir and a gas reservoir. A highly undersaturated oil reservoir versus a volatile oil reservoir, and for gas reservoirs, a gas condensate reservoir versus a retrograde condensate reservoir. Really, there's only one important point I want to make. If you have this situation, which is undersaturated. You can tell me why it's undersaturated.
Above the bubble point.
It's above the bubble point. So I can add more gas to the system and keep it a liquid at that pressure temperature. So it's undersaturated. I always like to think about the salinity situation. There's a certain amount of salt I can put in the water, okay, and then before it becomes saturated, okay? So it's undersaturated. Now, if I started adding gas to this system, what would happen is my phase envelope would start to creep up, right? Until I got to the point where it went right through that, then I'm saturated. So, if my reservoir starts right here, I no longer have an undersaturated reservoir, I have a saturated reservoir. It's day one. My reservoir pressure and temperature here. It comes to the surface. Does it produce gas?
Yes.
Yes. This is a low GOR, highly undersaturated. A lot of times we call them black oil, which is very little gas. Does it produce gas?
Brake oil?
Yes. Produces gas?
No.
Is it possible to produce a well that doesn't produce gas?
As long as you're, well, not theoretically it is.
As long as you keep your surface equipment above the bubble point line?
I think what you're talking about is this. You've got a point.
You can do that.
If your path of production
You can stop.
is there.
Yeah, if you could
Okay,
do that.
so that means the two-phase envelope for your system is below ambient conditions. Pretty tough.
Yeah.
As far as I know, no naturally occurring hydrocarbon system has a bubble point below atmospheric pressure.
Right. You'll always produce minimal.
Yeah.
I guess.
Think of 30-weight motor oil. That's pretty stable stuff. But if you leave it out in an open room for a long enough time, it evaporates.
Yeah.
Okay.
I was thinking something about being selfish. I was thinking, well, I can turn into sales and move the watt meter, and and maybe not do it, but it's going to have to go to ambient conditions sometime.
Yeah.
Yeah.
I think I gotta start checking this stuff. I think I ran out of batteries. Which means my voice won't get recorded. Now I can't tell if it's, I don't know.
Definitely not coming through speakers.
I think the only way to check that is back here in this mode. See my audio. I have to come back here to even see if my audio is getting recorded. That poor guy in Denver is going to just a disaster. Okay. now I can go through these fairly fast. A volatile reservoir just has a higher GOR. There's no, it's the same breed. Except for, man, those carrying batteries, and I took them out of my thing.
Which are they, what are they?
I think it. Double A.
I got double. How many?
2. See, as you know, I didn't use them much last year, so I'm not used to keeping these numbers. Got a light.
Yep,
I can hear it. So this is just something, this is the first class or first year I've taught with a mic. This one used to work for us real well, but when they checked out the new system, now if he was watching this live, he could call me and say, I can't hear you anymore. Okay, so the only point I made in this PowerPoint is that all hydrocarbon reservoirs produce gas, to my knowledge. So it doesn't matter whether we call it a black oil reservoir, undersaturated reservoir, saturated reservoir, volatile oil reservoir, a retrograde condensate reservoir. The only thing that's unique about a retrograde condensate reservoir is that it passes through the quality lines of the phase envelope, so that at some point in time it's increasing its liquid volume when it hits the dew point, because the liquid volume was 0. So it's increasing the liquid volume, but as it passes through that tip of that phase envelope, it can actually retrograde. Think about that retrograde motion of a planet. It starts going backwards. The liquid volume can actually decrease. So that's where the definition of retrograde comes from. But it's basically a gas reservoir. And why is it a gas reservoir?
This temperature and pressure on the inside is critical point.
It's just its temperature. Its temperature is greater than its critical temperature. So that when it hits the phase envelope, a bubble doesn't appear, a drop appears. Okay, that's the difference. So if you're looking in the laboratory at this fluid, if you're below the critical temperature, bubble appears. If you're above the critical pressure, drop appears. They all produce gas. But as we move to the right, the ratio, the GOR, decreases. Increases, the yield decreases. And I just have this one up there because it shows the quality lines there of a retrograde condensate and how you can pass through them. And then about gas reservoir. By and large, when I'm talking about the general case, this is what I'm talking about. A reservoir that out there is a gas reservoir throughout the life in the reservoir state. And I do this because it's the easiest case. If I actually have a condensate reservoir and my whole reservoir generates a liquid saturation in there, it changes the physics of my flow model, because I now have two-phase flow in the reservoir rather than single-phase flow. So I like to stick to this case as kind of the more general case. And this is from McCain. You hear undergraduate students use his textbook, so they've seen this slide before about how we usually can tell which of these regions we're in just based on the initial producing gas oil ratio and or the heptanes plus if you did a chemical analysis of the liquids. This
What
is,
is-
yeah.
What is your, like in your opinion, what's the main deciding factor as classifying something condensate or wet gas? Do you go by C6 composition? Do you go by I mean, I know there's a GOR, the color and stuff like that.
Well, that's why I got this next slide, is to answer that question. I do a study. Okay, so all the dots on this graph are overlaying a textbook exam. And the only way you know whether you're above or below the critical point is looking at it through the window by bringing this complete surface sample, a complete subsurface sample to the surface, putting it at reservoir temperature and pressure, and then bringing it below the vapor liquid equilibrium line. See, that's the whole line where there's dew point or bubble point, and see whether a drop appears or a bubble point. Okay, that's the only way you could know. So data I have on here are from the Eagleford chip, where we know we have a transition from oil to gas condensate to gas through like a 7-county area. We have that transition. So then, for future reference, based on everything I have right now, this Red Hills, this symbol up here is a different reservoir. But everything but the Red Hills is Eagleford Shale. So you can see that I can kind of draw a dividing line based on GOR for this reservoir. Okay? Now if I got something on that line right about here, I always got to remember that my students can't see that. I'm going to get a different color because I don't know whether it's if it's, you know, if it's in this area right here, I'm going to say go out and get a sample and run it to the lab. I don't know if that's condensate or oil. Because back to design, my reservoir performance for a reservoir is going to change depending upon whether I'm calling it a dew point reservoir or a volatile oil reservoir. But based on my study, if it's clearly to the right or left of that line in my study, then I'll make that assertion on a reservoir by reservoir or case by case basis. Okay, who wants to go home?
Question.
Yeah.
No one has to account, but can you last week you really quickly kind of went through pseudopressure and just the philosophy of why it's useful as a.
Now let's save pseudopressure until we get into chapter 6 and 9.
I was going to ask you to reiterate what you said last week, but I can wait before we revisit again.
I'll just say this. For liquid flow, we use pressure to just the pressure drop across the formation is the driving force. For gas, it's pseudo pressure. And that's because for liquids, it has very small gradients in viscosity with pressure. The viscosity doesn't change very much with pressure. With gas, and also with oil or liquid, the compressibility doesn't change very much. So when we derive the diffusivity equation or the characteristic fluid flow equation for liquids, we assume constant and compressibility and viscosity. We know with gas, these things change wildly with pressure. So we incorporate them into the pseudo pressure by integrating the changes in viscosity and the changes in compressibility with pressure. So we make up a new term called pseudo pressure for gas. When we get into 6 and 9, we'll use, it's not going to be any part of our test for chapter 1. We just introduced it.
I have one of those special questions.
You've been saying reservoir gas gravity a lot, or gas gravity, and we're trying to determine
Yeah.
the gas gravity in the reservoir, right? In the book or in the examples, they keep saying well stream gas gravity. Is that the same thing?
That's because these equations were invented by surface engineers.
But it's the same
and
thing.
the last time they saw it was in the well.
Right.
Okay? But when it gets to the bottom of the well, it's still the well stream gas gravity. When it gets out into the reservoir, it's the reservoir gas gravity.
So they're interchangeable.
Yes.
Okay.
Yes.
One way classify or identify the reservoirs whether the retrograde condensate or dry gas or oil is just by applying their phase diagram. We can classify what kind of reservoir is. But can we figure out the type of the reservoir? Physically see that taking sample from separator or from the wellhead. Can we classify whether it's a gas condensate or the retrograde condensate? While if it's producing only gas, we can say this is a dry gas. If it is producing gas plus condensate, we can say this is a gas condensate. Can we have certain parameters by looking at those? We can say, these are the, this is a retrograde condensate.
Yes. Next question. Yeah, you've got to do a study. In maybe some parish in Louisiana, if the color of the oil is strong, it's always a condensate, and if it's green, it's always an oil. But that same rule of thumb may not hold for Wyoming. Universally, any combination of hydrocarbons could exist, and they do. The mixtures vary widely from the Middle East to Alaska to the Gulf Coast. So you have to do a study. If you, for your area, want to know, once you drill a well, whether it's a condensate or an oil, you have to look regionally on what are the indicators. It could be the color of the liquid. It could be the API of the liquid. It could be, like I'm trying to do here on this study, primarily based on the GOR. There's not a universal answer because because the mixtures, and I'm going like this because what I'm emulating is the amount of methane, ethane, and propane. And they tend to, each higher hydrocarbon tends to have less of a concentration, but they tend to almost be a straight line, okay? And this all has to do with fluid characterization. That's kind of the slope of that line. And it's how they do fingerprint analysis on whether a certain formation has the same fluid as another one, or two reservoirs are continuous. They can fingerprint these types of fluids. But I'm not sure what your question is.
The question is really, can we figure out that by looking at certain parameters, like whether they are the separator conditions or the wellhead parameters, that this is a retrograde condensate reservoir. To identify retrograde condensate reservoir, can we use these surface parameters? This is the one way we can figure it out.
Only if we can benchmark them back to actual laboratory data. Now, if it doesn't have any liquid yield, it's obviously a gas reservoir.
No, if there is a reservoir which is producing, which has a certain yield, it may be a gas condensate or a retrograde gas condensate.
You can't tell without doing a study. You can't. Okay. I thought I was making that point. I thought I was making that point with this slide. You have to do a study. This is why I like petroleum engineering. It's because it's like food or cooking. It's an infinite body of knowledge. There's infinite combinations that exist out of there, not only the reservoir fluid, but the geologic formation. And not only the lithology of the geologic formation, but its temperature, its angle of inclination, etc. So, for people that want answers, you belong in mechanical engineering or chemical engineering or some of these things that have the exact answers. And what I tell people all the time is we don't know anything to maybe one significant digits, and sometimes we don't know it within 1 or 2 magnitudes. So don't try to pin me down. Okay? All right, I'll see you next week. You can have your batteries ready. I need to close down. Stop.